Okay, so esters are made by reaction of a carboxylic acid with a, so I'm going to do, let's do a real ester. Let's do this ester. Let's do pH, that's phenyl ring. So this is the ester of ethanol and benzoic acid. So our products need to be okay. So okay, think about it. What's the other product over here if we do that reaction? How do we clip those things together? There's another molecule over here. Water. By the way, that's often a very good answer, right? So, we talk about this being a hydrolysis reaction. We're going to break some bonds and we're going to add water. So, one of the H's is going to go on this O, and the OH is going to go somewhere else, right? You see, that's how these things are made. So what I'm going to do now, we can make these things through acid conditions. Acid, we can go both ways very easily, both ways, okay? And when we make an ester, we start off with a carboxylic acid and an alcohol, and we do it in such a way so that we can remove water so that we can get to this side. If we want to hydrolyze an ester, we just make sure we have lots of water under acidic conditions, and we would go the other way. That's just first year chemistry, Le Chatelet's principle, okay? So that's the other thing I do like to point out. Remember, intro chem, 1, 2, organic 1, this is organic 2. You're building your arsenal of chemical knowledge so upon each other. So you need to know those other things to some extent, and we review it. But I'm going to do the hydrolysis of this not under acidic conditions, but under basic conditions. For acidic conditions, it's acid catalyzed. Under base, we talk about it being base induced, and you'll see why in just a second. So we're going to do this reaction, and the base I'm going to use is sodium hydroxide. Okay? So sodium hydroxide, it's not going to act as a base, it's going to act as a nucleophile. What's the first step in this reaction? It's just the nucleophilic attack of our carbonyl carbon. When we do that, we get tetrahedral intermediate. And our tetrahedral intermediate is going to reform that carbon-oxygen double bond. If we kick off ethoxide or hydroxide, we're going backwards, okay? That happens. It's going back and forth, back and forth, back and forth. But it can also kick off this thing, okay? Now, I'm not going to draw the reverse reaction because the reverse reaction is very unlikely to happen. Why is that the case? Why is the reverse reaction unlikely to happen in this case?
Acid-base.
Acid-base, strong base, carboxylic acid, boom, this thing's very thermodynamically favorable. This is just going to pull off that, and it's going to form this. Just going to sit there. This is the type of reaction I could start it, go to lunch, come back, and it's going to be over there, right? I want that up there. What do I need to do to get up to the top, to get to the alcohol and the carboxylic acid? All I have to do is add a strong acid like sulfuric acid, nitric acid, HCl, any of those. I would just quench this reaction. Strong acid, a full equivalent or more. Typically what we do, we just throw a whole bunch of acid in, we don't care, and we get to there. So keep in mind this, I'm going to erase this now and I'm going to construct the energy diagram for this particular reaction. We're going to talk about what drives this reaction, okay? And this is actually right out of the slides. We did talk about this in class, and I think one of the things that's good about midterms is you guys listen a lot more attentively when I'm talking before a midterm than every Monday, Wednesday, and Friday morning, which makes sense. Okay, so for our energy diagram, this is just energy. Maybe it's enthalpy, maybe it's internal energy, maybe it's delta G. Doesn't matter too much. Actually, I'm going to say it's delta H. Enthalpy. And our products are here in energy, and our products are pH, our ester, okay, water, sodium hydroxide. I'm sorry, our reactants. Our reactants are this energy. The first step in the reaction is forms, if we remember, we formed the tetrahedral intermediate. It's going to be higher in energy because it's an intermediate, okay? And then it's reversible, but then, and we have Na. We don't really need H2O. It's not actually doing anything. But our Na plus just stuck around and didn't do anything. Only the OH did, okay? So all those things are still there, and now when we kick this off, and we kick this off, we go to pH. Now this is actually good. Here we have an OH minus. The only difference is we still have our Na plus. Water's around. I didn't even really need it there, but water's around. Do you think that's higher in energy than here or lower in energy? This is going to take a little bit of knowledge of the only thing that's different. Well, there's a couple things that's different, but one thing that's different is we have an OH here. We have an ETOH over there, ethoxide. Ethoxide's a little bit stronger base than hydroxide. So this is probably going to be a little bit higher than energy than over here. I'm going to put it, I don't know, but it's going to be close, okay? And we kind of think we're done here, but we're not. We're not done because this next reaction, where we pull off this proton, this is what drives the reaction. We have all those other things. This is the part that's really exothermic, because now our base is a very weak carboxylate base. And like I said, reactions like to go, we say, downhill. They want to go to the most energetically favorable place if they're all equilibrium. And this is why this reaction doesn't go back, is because that is very unlikely for, even though it's an equilibrium, it strongly favors over there, the acid-base equilibrium. Strongly favors the carboxylate anion and the ethanol than the ethoxide and the carboxylic acid. Okay, and then we just quench it to finish it off. We say we quench with H+. Okay? So there's an instance of, I would expect you to be able to get most of these rates. I'm not going to care too much if you have this a little higher or a little lower. That's not important. It is important that that is higher, the tetrahedral intermediate is higher, because that's an intermediate. And not only that, here we have carbon-oxygen double bonds. They're strong bonds. That's why this is a little bit lower in energy. But the important part here is this is very much exothermic, okay? That's what drives the reaction.